Good morning. Let's speak. Good morning, everybody. I think we can start our lecture. Everybody is here. Today we will speak about characterization of contaminated environmental samples. But as I understand, you got two lectures of characterization of different samples. It was a lecture of non-destruction analysis by Sergei Baidakovsky, told about gamma spectroscopy. It is the first method of characterization of any contaminated samples. And it was destructive analysis with some written warning. But today we will talk mostly about the local microanalysis to reveal the forms of radionuclides, to choose the proper way of decommissioning, the proper way of management of the radioactive waste, and rehabilitation contaminated territory. So, characterization of contaminated environmental samples in the nearest zone of nuclear legacy site or some source of contamination is a very complex problem because the objects are heterogeneous. Contamination could be distributed in unknown places in the most cases. So we ought to know. So there are some examples of nuclear legacy sites. It is a former reactor which was stopped and is to be decommissioned. It is a nuclear site for nuclear tests. It is Lake Karachai, one of the most contaminated of high radioactivity place of liquid radioactive waste. There are tanks, sufficient tanks with liquid radioactive waste. All of these objects are to be decommissioned and rehabilitate the territory around it. And the questions are to be answered are how is contamination is distributed in a landscape scale and at the macro and micro level. And if you know this, if you have this knowledge, you can choose the proper way of management. You have to know what is the speciation of main radionuclides, what are the forms of these radionuclides. And the problem is how to perform sampling to reveal this picture properly. What is the reason for characterization of contaminated radioactive samples? If you've got some radioactive waste temporary storage, or contaminated soils, or some nuclear legacy site, you are to perform some actions to rehabilitate territory and to manage with this waste. The first question is, what are the forms of the main radionuclides? In some cases, you can take all this waste and put in a special place for radioactive waste. In some cases, you are to clean this soil, and it would be pure. You can use it in your agriculture or some else. So selection of the optimal path for territory rehabilitation, soil cleaning is another step after the knowledge about the forms of radionuclides. It is the main idea of this lecture. If you are to choose some methods of characterization, you have a lot of different devices how you can do it. And the question is how to obtain the maximum information with the least cost, because you can use synchrotron radiation source, or you can use a laboratory device for the same thing, for tomography, for instance, or you can use XRD device laboratory or synchrotron, and you can use transmission electron microscopy or some other advanced techniques as it referred to. Yeah. So why non-destructive characterization is the first point of any characterization? Because we are to know the forms of radionuclides. And if you destroy your soil, if you leach it, you can lose the initial forms. So gamma spectroscopy is the first method of non-destructive characterization. But you know about it, everything, I think, after the practical lessons by Sergei Baidakov. Today we will speak about local microanalysis. It is photoradiography to reveal the heterogeneity on macro and micro scale. Micro-Raman spectroscopy to phase analysis. It is very convenient method. SEM method to reveal morphology, size, and elemental composition at micro scale. X-ray tomography to see density distribution in the space in 3D, in some soil or some other objects. And some other microanalysis you can use, diffraction, fluorescence, and absorption of X-ray, and not just non-destructive, but we can refer mass spectroscopy with secondary ions to very small destructive method, because it destroys only the upper part, the surface of the sample, but it can show you isotopical composition of this sample. It is a table just to classify different methods. There are a lot of methods. If you know the acceptation and recording of signal, so there are passive techniques without acceptation. Photons, excited methods, methods with thermal neutrons, electrons, and multiply charged ions. This is excitation of our signal. You have unknown sample, and you are to know what is it inside. What is the elemental composition? What are the species of radionuclides, and some other information. So What about the registration of signal, the recording of signal? You can register photons, electrons, and protons, alpha particles, and multiply charged ions. It's a very simple classification, but it helps us to understand the position of each method in this big family. So all the methods of nuclear spectroscopy are passive methods. Gamma spectroscopy, liquid scintillation counting, alpha spectroscopy, and different kinds of photoradiography. We don't induce, we are not to induce this signal. It is inside our sample. Alpha activity or beta activity or gamma activity, and we can record them. If you use photons, we can see different, the family of X-ray absorption, spectroscopy, X-ray fluorescence, X-ray diffraction, Raman with laser and infrared. And if you use photons for exciting, you can obtain the information from X-ray photoelectron spectroscopy and ICP-MS with laser ablation, gamma radiography, induced, if you induced fission by gamma photons with high energy. If you use reactor with thermal neutrons, you can obtain neutron activation analysis. Sergei Baidakov told about this method, and you can perform alpha radiography on the basis of nuclear reactions like neutron alpha and fission radiography. And with electrons, we can obtain information about elemental composition using EDX SEM and Auger electrons and transmission electron microscopy. And at last, multiply charged ions used in some cases for PIXI, particle-induced X-ray emission, and mass spectroscopy with secondary ions. I should tell about some of these methods very briefly, I think, because I'm not sure that it is very important for the first characterization, but some of the methods are used, very common. Distribution of radioactivity could be homogeneous or heterogeneous. But a common assumption in radiochemical analysis is that the radioactivity is distributed homogeneously. Is it always true? Let's see, here it is the nuclear melt glass aggregate, the result of ground nuclear testing, and it contains the most part of the radioactivity in this sense, if it is nuclear testing. Ground test, for instance. There are a lot of examples when radioactivity is not distributed homogeneously. So local distribution methods are applied to study the forms of radioactivity release in the environment, for instance, radioactive particles, to study technological samples, spent nuclear fuel immobilization, waste disposals, and it is used for nuclear forensics to prevent smuggling of radioactive and nuclear materials. So let's see on passive techniques. How can radiography be useful for waste characterization? Radiography could show you the distribution of radioactivity in waste at macro and micro level. And I will show that sometimes it could be really macro level. Radiography is the best tool for searching sites of local concentration of radioactive contamination. The problem is that you are to analyze the most contaminated part of your soil and the least contaminated to see the end members of your radioactivity. And you are to choose this, the most active and the less active parts of some contaminated object. And radiography could help you. And you could estimate the total radioactivity and the alpha activity separately. if you use different kinds of radiography analysis. Why is it so important? The fact is that contaminated soils, in the most cases, has radioactivity due to fission products like cesium and strontium. It is today. But if you see to hundreds and thousands years to the future, because we are to think about our future generations, you can think about alpha activity mostly, long-lived actinides and some else. And you are to separate, because if you have a simple radiography of the total activity, cesium and strontium are the main contributors to the result. And if you use only alpha track radiography, for instance, you can see only plutonium, uranium, neptunium, and americium. And you can think about the long-lived actinides, which would be for, I cannot say forever, but many thousands and even millions years. About another classification of all methods of characterization. Methods of characterization of different samples according to their basic principles and way of presenting information could be divided to three big groups. Methods of imaging and visualization. It could be imaging not only like X-ray picture, it could be elemental map, which show you the distribution of elements in the sample. So imaging and visualization. Spectroscopy group of methods, when you got a spectra and obtain information from spectra. And the third group is diffraction and scattering methods. You can obtain different kinds of information about phases, phase content, and the size and shape, if it is scattering, the shape of the nanoparticles or some microaggregates of this matter. So about radiography. The main part of any radiography system is detector. Detector is to be sensitive to radiation with special resolution. Not for bulk sample, but special resolution in 2 dimensions. You can find local places, local points of high radioactivity using radiography detector. What kind of detectors are in radiography? They are storage detectors and detectors in real time. The most old detectors were with chemical pretreatment. There are photoplates, X-ray films, nuclear emulsions, and solid-state nuclear detectors for charged particles. You know that the phenomenon of radioactivity was discovered using photoplate by Henri Becquerel. So it is the first method to see, to reveal, and to visualize the radioactivity. And other group of storage detectors are laser-induced luminescence detectors, like imaging plates. Yesterday you saw these imaging plates. And other group which has higher cost, and it is used in medicine, but in science it is not so usable. Detectors in real time. It is useful for biology, for medicine. You can see the changing of radioactivity in your object. For our soils, it is not so important. The basic principle is semiconductor diodes and solid-state scintillators. We use in our practice solid-state nuclear detectors for alpha particle analysis and autoradiography with imaging plates, storage phosphor screens. So these two ones, we can reveal heterogeneity of radioactivity distribution using computed radiography with imaging plate, which reveals alpha, beta, and gamma, and X-rays, and any other kind of radiation. And alpha track radiography only for alpha particles. Advantages of auto radiography with imaging plates is that this kind of radiography could help us to optimize sampling process. Because destructive methods of radioactivity analysis needs around 1 gram of material, and radiography could help us to choose the proper representative samples. And it could detect hardly determined beta emitters like tritium, radiocarbon, strontium, and some else. This is the imaging plate. You saw it yesterday. It is the opposite side, black, plastic support. This is the working side, blue. It has sensitive layer which collects energy and radiation data. It contains of the crystals of barium fluorine bromine doped with europium 2+. When you are to know the distribution, to reveal the distribution of radioactivity, you place your imaging plate with the different sample in close contact in the darkness, because it is very sensitive even for light. And after some time, you can obtain information. So the first part of the imaging plates system is detector. The second part is reader, laser scanner, which use laser source which stimulates photoluminescence in sensitive layer. And the unstable europium 3+, which was formed under the radiation of your sample, goes back to the initial state. And simultaneously, you've got photons which are collected by photomultiplier tube. And after that, we could visualize the result, the obtained image, using special software. This is the scheme of this imaging plate working: exposure, reading under the laser beam scanning. And after that, you can erase this information with visible light and use this imaging plate again. If you want to know physical principles, it's very good paper for it. Some examples of using of imaging plate. If you've got a soil, it is the soil from semipolite nuclear test site. You can see down some soils. Here they are, and a special grid with cesium ink. This ink could be visible on the photo, and it could be visible on the radiogram. It is radiogram. You can see some hot spots, and you can measure its activity. It is not just spectrum, you know. We cannot obtain information about the identification, exact identification of radionuclides, but you can compare different particles to take the particle of interest for further analysis. There are digital luminescence units intensity, so it is some data which could help you to compare different particles. And you can localize the most interesting particles using this thing. And I would like to say that the preparation of samples for this method is very simple. It's just some soil which is put in close contact with this imaging plate. And the same thing is with the filters, resolve filters from the object shelter from Chernobyl reactor. The idea was to find some particles. And you can see that these filters are of different size of particles which could come on this surface. And this is the result of 15 minutes of exposure time, and this is around a day. And we can find the most radioactive filter in this sandwich. This is an example of some plants from the lake P17. It is from Mayak Production Association. It is a place of storage, temporary storage of liquid radioactive waste. And in this lake, there are some plants like this. And you can see it's a radiography picture. This is the soil from Chernobyl, not far from the reactor. You can localize the particles and take it for SEM and other analysis. So you can cut the initial soil preparation to better finding the particles of interest. And the comparison of digital luminescence units of different particles help you to find the best particle for further analysis. And you can control any actions with your sample. You can cut the filter or some paper, some jumped particles from the lava, Chernobyl lava heap. It was a planche with the paper, and we find some jumped particles on the surface of this paper. You can be sure that you will find your particles even if you make something with this preparation. And after that, when you localize some particle, it is the jumped particle from Chernobyl shelter, you can use a special device to perform XRD, SEM, and other analysis. And I would like to show you the example of really macro analysis using radiography techniques. It was some work. Here it is the paper. They got some contaminated device. It was some plant, I don't remember exactly. They got saline, walls and floors contaminated, and distribution of this contamination was unknown. They used 1,000 of autoradiography imaging plates. Here it is wall, and you can see green pure from contamination, and orange has some contamination, and the most is red. So they are not to put all this wall to the radioactive waste. They could localize some places, small places of this contaminated wall. The square width is 250 square meters, this big square. And they've got 2D mapping of these traces of radioactivity on the scale of meters. You see advantages of this radiography with imaging plate is simple preparation of sample for analyzing. It could be filters with colloids, it could be aerosols filters, it could be soils, sediments, and biota, and some other samples. We've got express results using this radiography techniques. And you can cut your sample preparation and repeat again to be sure that you did not lose the interesting particles. Disadvantage is that the information is not forever in this imaging plate. 2-3 days is okay, but after that, it is a fading of this information. So it could not be a very low radioactivity in your sample. As it is for alpha track radiography, you can use exposition time weeks or month if you have this time. In this case, it could be only 2, 3, 5 days and not more. So low activity, not correct for detecting. Limited period of time from exposition to scanning. And the main contribution to the imaging plate is beta activity. Alpha track radiography. You can see this picture. It is alpha tracks on the solid state emitter detector. Simple preparation. You can use wet samples, no darkness. It could be on the open air, open light. Any exposition period of time. It could be minutes, weeks, months. Low activity could be detected. No fading of alpha tracks with time. And it is not expressed method because we are to perform some chemical etching of the detectors because the traces of alpha particle is nanoscale. You can see it using transmission electron microscopy, but it is not convenient to use such a device for radiography. So this picture you can see at optical microscopy, simple optical microscopy. It is the result some hot particle which has such cluster of alpha tracks from the center. You can see the scale of this picture. Sometimes you've got some contaminated soil and you are not sure. In this case, it was bottom sediments Yenisei River, not far from the combined Железногорsk, and sometimes there are some release of radioactivity to this river. So we are to find hot particles which have technogenic origin. But you know, if you use fission tracks after neutron induce after reactor, you can obtain the information about natural minerals like zircons, apatite, because they got some uranium in its content. And uranium could has a fission process after reactor. How to separate plutonium 239 from uranium 235, which could be natural. We use together alpha track radiography and fission radiography. And the cross section of plutonium 239 and uranium 235 is just similar, around similar, but the period of their life is very different in many orders of magnitude. And so if we compare alpha track results and fission track results, we can review the particles of artificial origin. Using special standards, you can identify the radionuclide using alpha track radiography. It is a kind of alpha spectroscopy without leaching, because the energy of alpha particles is different. You can see americium 241, plutonium 239, and uranium 235 is the low energy, it's middle, and it is high. So the size and morphology of alpha tracks of this etching after etching is different. And you can use special standards and try to identify your alpha emitting nuclides in contaminated soils. What other information you could obtain from alpha track analysis? You can see the size of particle, because here you can see that alpha particles will go to the detector just in that way, goes from the particle. If they come to the sides, it is not the center of, it is not the source. So you can obtain the specific activity of a single radioactive particles and the distance from the particle to the detector surface. The fact is that it could change because it was a special software to obtain it, these parameters. Let's go from radiography to other micro-local analysis methods. I would like to begin with Raman spectroscopy. It is very simple. It could use some. I would like to begin from advantages. It is express method, not destructive, and you can use transparent matter. If you have very contaminated sample, you can put it into the glass vial and come to Raman spectroscopy. And then using optical microscope, you can see the Raman spectrum from your sample, not from glass of this vial. And we have seen in France, in Marcoule, they use Raman spectroscopy just in hot cell. Microscope is inside hot cell. Raman spectrometer is outside. Optical wire. It's very convenient, and they can see some fuel rods after neutron. So it is spent nuclear fuel, and you can obtain the information about your two state. It could be dioxide, or it could be oxidized, more oxidizing state, and the shape of Raman spectra is like fingerprint. If you got good library, you can see you can obtain the information about the oxidation state of uranium. Wow. This is an example of the fragment of Chernobyl lava-like radioactive materials, which is close to lava because it is a silicate matrix with uranium and zirconium. And during cooling, some crystallites formed inside this glass matrix. And we've got characterization of different crystallites inside this matrix and of this glass. It is glass, it is uranium dioxide, and this is zircon, so-called Chernobylite. It is very high uranium, zircon. Zirconium, CO4. Okay, this is about Raman. Let's go to electron microscopy analysis. It is the most common method for characterization. It is not very representative analysis because you see only small part of the sample. You cannot say that it is for raw soil. That is why at first it is better to use radiography and gamma spectroscopy to find the most contaminated part, and then perform electron microscopy. The basic principle is very simple. You've got an incident beam of electrons. In the case of scanning electron microscopy, it is around 20 kilovolt, different voltage, accelerated voltage. In the case of transmission electron microscopy, it is around 200 kilovolts, and it is a sample. In the case of scanning electron microscopy, it is not transparent. All the information you've got here to the upside. In the case of transmission electron microscopy, direct beam comes through this sample, and you can see electron energy loss spectroscopy and EDX, like in SEM case. And here you can see backscattered electron mode picture, which is sensitive for Z contrast. I will show you the examples. And morphology is better to use secondary electrons mode. Characteristics X-rays, it is energy dispersive X-ray analysis, elemental composition of your sample. This is an example which show you the difference, because secondary electron mode, it is the same part of the sample, and a backscattered electron mode. This is uranium particle which could not be seen using secondary electron mode. It is very convenient to find, to localize the particles of interest. Except picture, except imaging, scanning electron microscopy provide spectrum, elemental spectrum of characteristic X-rays, and you can perform electron backscattered diffraction for phase analysis. It is important. In some cases, it is important to know what is not only elemental composition, but what is the phase of the sample analysis. Some examples of scanning electron microscopy images. It is fuel particles from Chernobyl. They are very they have different morphology. As in some cases, it is close to the fuel grains. In some cases, they are another particles, and elemental composition is different. It could be a uranium zircon with different ratio of uranium to zircon. This example is a particle which came from the place of melting of uranium rods, uranium dioxide rods with zirconium cladding. And here you can see the fuel grains which were not molten, no melting you can see, but this is the channels for fission products, volatile fission products, which came from the fuel during the operation of this reactor. I would like to say that the burn-up of this fuel rod could be seen using this morphology image, because the pure fuel grain is without these channels, and more higher is burn-up, more channels you can see, and it is the reason for destruction. If it is the particle from the environment, so if burn-up was higher, this particle will destroy in more extent than pure grains of fuel. This is the example of jumped particles from the lava-like heap. And morphology is very close to lava from volcanoes, which came to the sea. There are the same bubbles, gaseous bubbles. And this is the jump particles from the lowest floor of Chernobyl reactor, which was covered with water. It was the basin barboton, and that's why such a morphology, because lava came to the water. It is not only glass matrix, it has a lot of uranium O2 dendrites. And in some cases, you can see uranium secondary minerals. If in the matrix uranium is tetravalent, in these secondary minerals it is uranium-6, so it could be it is much more soluble, and it could migrate very fast. You can see that morphology of nuclear melts from ground testings is not the same as Chernobyl particles. It is environmental particles on the semi-volatile state side. And you can see the traces of molten, of some bubbles, but it is not the same as fuel. And it is not uranium, it is just silicate matrix from, it is the content, elemental content, is very close to the sands of this test. Just sodium, silicon, aluminum, and so on. Radioactive materials is very low in concentration, but could be very high in activity. And it is inside this very hard particle. It is difficult to cut it. Trust me, it's very difficult. It is very high temperature of very short duration. In the material research science point of view, it is very interesting matter to study, because you cannot repeat these conditions in the laboratory, in your laboratory. Very high temperature of very short duration. It is impossible. Only there are some impactides when the meteors falls down on the Earth's surface, maybe some similar objects. There are some synchrotron-based techniques to reveal the speciation, the phase content of your matter, radioactive matter. It used for environmental analysis, it used for nuclear forensics analysis. To prevent smuggling of radioactive and nuclear materials, you are to study some objects which were found somewhere. So it is microxanes and microexaves and X-ray fluorescence for elemental composition, X-ray tomography to reveal the space distribution of density. This is micro-XRF of the bottom sediments from Mayak Production Association storage of liquid radioactive waste. You can see elemental map of uranium, calcium, iron, and uranium is not bound to something like calcium or iron or some other elements. It is SEM image and EBX spectrum of the same particle. And this is another example of the same bottom sediments, and microxanes shown that it is uranyl particle. It is uranium-6, and in this case, I'm sorry, this is uranium-4 and this is uranium-6 particle. So the oxidation state and migration behavior of this uranium could be different. What is xanes and exaves? It is the two parts of the same spectrum. X-ray absorption spectroscopy could give you different information about the oxidation state of the element of interest. This is just edge of the absorption edge, and you can see the local surrounding of the atom of interest. You can see if it is. You can find the structure of this material. This is some examples. It is dioxide of uranium. It is uranium-308, and this is stopit-like uranium of very oxidized from the same place. Just there are different particles from the Mayak production association bottom sediments. This is an example of X-ray tomography from Chernobyl lava. And this color means only density. It is not the identification. It is a beautiful picture, but we don't know what is it exactly if we if you have no information from scanning electron microscopy, from XRF and other analysis. So one method, even if it is very beautiful and advanced technique, could not give you all the information about this method. It is better to use different methods to have all the information. Some words about mass spectroscopy with secondary ions. It is not non-destructive because some surface is destroyed. This is the primary beam, and this is the secondary beam, which is collected and analyzed, not only for nuclear forensics. I've got some example from environmental studies using mass spectroscopy. It was very interesting study. So the basic principles is that you've got some primary beam. This is the sample, and the secondary beam goes through some magnet system to the analyzer, and you can, in some cases, you can simultaneously record, register different mass to charge. It is not identification of uranium. It is only the mass 234, 235. If you've got, for instance, there are some problems with mass spectroscopy because you can overlap plutonium-239 and uranium-hydrogen 239 ion. But there are some methods to obtain good results, even in that case. This is like Lake Karachay, which is now closed, but this work was done around 10 years ago, maybe 7 years ago, and underground groundwater goes to the south. And there are a system of wells from which we got some water, groundwater, and after a filter of this water, we've got the distribution of plutonium, uranium, and neptunium to different sizes. It is red is 200 nanometers, and blue, dark blue is soluble form, and blue is around 3 kD. It is just not soluble, but very small colloids. You can see that uranium and neptunium are soluble mostly. This is the distance from the Lake Karachay in kilometers, so to the south. And plutonium is mostly in colloids. And if you go from the source, the colloidal form is predominant. It is not good, because colloidal form, as we know, can go faster than soluble sometimes. This is mass spectroscopy secondary ions analysis with nano resolution. And this mapping could show the binding of plutonium to and uranium to some natural particle of colloids with manganese and aluminum and iron, not calcium. This is an example of environmental analysis. Sometimes we are to use mass spectroscopy for some forensics analysis. We are to know the source of particle. And according to some isotopic information, the ratio of plutonium 240 to plutonium 239, we could reveal the source of this particle. If it is reactor or some weapon test, and here is the difference of plutonium, different plutonium isotopes can show you the power of explosion if it is nuclear testing. It is evident that it is different. And if you compare these results of nuclear testing with Chernobyl, you can see the difference of plutonium isotopic ratio in these cases. So conclusions. The most informative non-destructive techniques for contaminated samples characterizations are autoradiography. It is the first step after gamma spectroscopy, of course. You can reveal the distribution of radionuclides in your sample, and you can obtain the result from big massive of contaminated region. Electron microscopy could show you the morphology of the most high active particles and the main elemental composition of the waste. X-ray techniques of different kind is useful for structure analysis, local surroundings of atoms, if it is X-ray absorption spectroscopy using synchrotron radiation light. You can show, you can know the valence state of different radionuclides, and you can perform 3D tomography of the samples. And Raman scattering is very important, very interesting, very convenient for phase definition using a fingerprint with some library, and you can use even glass vial for your samples. And after that non-destructive analysis, you can use the next step, destructive methods, including sequential extraction, which can show you the extent of if this radionuclide is leachable, is soluble, and what is the extent of its solubility under different conditions. And you can choose the reagents for cleaning, or you can manage this waste another way. Maybe it is better to take it as a whole and put to the special place for radioactive waste. I think that it's all for today. If you have any questions, I would be pleasure to answer them.
So, same instrument is very expensive.
Scanning electron microscopy, you mean?
Secondary, yeah, secondary ion mass spectroscopy.
Mass spectroscopy.
Secondary ion.
It's
very expensive, and globally there are countable instruments. In the whole world there will be 17, 18.
It is a special instrument.
Very expensive and very huge.
Yeah.
But it is destructive in nature, like we understood. So
it's
when
not-
we can
not
use that?
this-
So when we can use, like you said, or we have to fast gamma spectroscopy and then all non-destructive techniques. So when we use this destructive method, then
Destructive.
SIM is a destructive method. SIM
Seems
is a destructive because we destroy the upper surface.
we destroy the surface,
Yes.
only the surface.
Yes.
But it is good because it is with micro resolution. You know, it is ICP-MS analysis.
Yes.
It is reaching all the sample. But in the case,
So when we can use SIM, like you explained,
SIMs?
yeah, when at which situation scenario we can use SIMs?
it depends on your task. If you work for nuclear forensics, you cannot work without SIMs because isotopic ratio is the main thing.
But at the end, it is like
But
you
if
say
you-
in the receiver. Can
Yeah.
we go to the SIMs picture, please?
SIMs picture, just a minute.
Yes, yes, yes. So when it is receiving on the right side, there is a overlapping. Yes, in the registration. No. Yes, on the registration, there are isotopes. They have a similar, and that confuses. If it is
There are different ways to. If you got, for instance, uranium matter with very small amount of plutonium, lower in some orders of magnitude, it is a problem. It
so
is
what
a
to do
problem.
next? I mean, in this scenario, what to do next?
And the next,
I mean, in this scenario, the
Yeah.
problem, how to deal with that?
you can see that we used not the main isotopes of all elements because the signal was very high for these elements. But here we can see it is very good machine, not just like this. It is Kameka nano SIMS confocal. Primary beam and secondary beam are in the same direction, and they can separate uranium and plutonium. It is very high cost of this machine.
Yes.
Yeah, nano SIMS.
But they have interference.
Yeah,
Exactly what you
Yeah.
say, because of the primary and secondary beam.
yeah.
They have confocal, so they
Yeah.
have interference, and then
Yeah, they have no hydrogen, uranium hydrogen ions. It is very good system for stripping the ions. So we got only uranium without, it is not multiple ions. And we can separate uranium 238 from plutonium 239. But right here, it is very high cost, and it is not
maintenance cost also.
so
is-
important for convenient for use if you have only contaminated soil and your task is just to clean it. It is very precise tool. It's very precise tool for some forensics analysis.
I have another question about the groundwater. The next picture, please.
About
Groundwater.
about what?
The groundwater.
Groundwater.
Groundwater. I understand.
Yes, yes,
This
yes,
one.
yes.
Yeah.
So I couldn't get what exactly the message was. These are the points of groundwaters in the vicinity surrounded by the basin.
This is a position of wells,
Groundwaters, yeah.
groundwaters. This is the distance from Karachay Lake. Just these wells.
Where is that location, Karachay?
Karachay, here it is.
Okay.
It was closed not totally at that time, but now it is closed totally. But the water in it has very high salinity, and it is very heavy. It goes to the groundwater.
This saline then gets
Nitrate, very high nitrate content.
So my question is, how we monitor from the groundwater well? What is the whole concept of measuring this?
The whole concept is that we got a lot of rivers, creeks, and lakes, and the groundwater will go to this river. It is only the question of time.
Because the graphs is does the groundwater level is minus with this graph?
Groundwater levels.
Because every well has different groundwater level.
Yeah.
That should be eliminated before plotting.
Yeah, but very close to this place, there are some intake of water to the surface. It is not just here, but any groundwater sooner or later will come to the river. It is a problem. And we hope that the water will be diluted during this coming. Some of radionuclides could soak on the surface of this sands, of this groundwater. Some could dilute by this. So it is a very great problem here. Very great problem. Because
people use this water for drinking purpose?
No, of course not. All of this place is a territory of production association Mayak. It is not a place for living. It is only some plants here. This is basin number 17. I thought about some plants in it, contaminated and bottom sediments. And here there are some manufacturing devices, and it is working now. So it is closed, of course, for person. This is not for environment, but groundwater could come anywhere. It doesn't stop by your. You understand? It could go through. This is the problem. Of course, not for drinking. Of course.
I have another question. If you have time.
We have time, yeah.
Okay, so the Chernobyl lava and plutonic lava, you made a very good correlation. So the difference is in plutonic lava, they get so immediate, the temperature gradient immediately decrease in plutonic lava. But that was not the case in Chernobyl.
Yeah, Chernobyl lava for some days.
Yes, so the crystallinity, the crystallization is a direct function of the temperature gradient.
Yeah.
So how we can correlate the Chernobyl lava
with nature?
With nature, yeah. Because you made a very good correlation about that.
Very good correlation. Sometimes we can compare them, but the content is very different. You know, around 190 tons of uranium and something like that of zirconium was in this reactor initially. And the most part of it is in this lava. Some part is in some heaps, maybe under the construction materials. But here it is silicate matter, which was melted together with this high amount of uranium and zirconium. That's why these crystallites formed, because they cannot be in matrix. Glass cannot be with so high content of uranium and zirconium. So it is formed zirconium oxide. And it is very interesting that this zirconium oxide is not monoclinic as usual in the environment. It is tetragonal and cubic because it is doped with uranium. And it is a problem because the transformation from cubic to tetragonal to monoclinic is with space expansion. And it could be the reason for destruction of this matter. At first it was very hard. Now it is not so hard, and it is covered with some yellow minerals of uranium, of secondary uranium-6. With natural lava, there are some similarities, but not very big.
The gradients are different.
Sometimes in volcanoes, you also can find the place of some melting for some hours or some days. It could be.
The crystallization is not feasible.
Yeah, crystallization not visible. Usually, yeah. Only maybe microcrystals. Yeah.
In your facility, do you have seen in your facility here in MSc? Do you have seen instrument?
SEM or SIMS?
SIMS.
SIMS, not here, not here. You have to have very good operator for SIMS. Not only machine, but a person who knows how to work in.
Thank you.
So maybe there's no question. We can have a break.
Yes, well, thank you.
Yeah.
Which type of sample we can analyze?
It's not interesting or solution, because the solution of radionuclides is homogeneous.
Okay, how can they produce prepared sample?
It must be flat. It must be flat. Even like a soil, it must be flattened. And to prevent your imaging plate from some problems, you uncover the soil some very thin film here, but very thin, because you want to see not only beta but alpha particles. Yeah. You can use very thin film, which can only take less over the alpha activity energy. And that is why you don't lose the matter. You say, it should be filtered with soluble matter. And if you have water, you can filter it. And this filter show you particulate matter.
Yeah, I see.
Because water, what is the problem with water? It is the homogeneous matter.
Yeah.
And radiography is not of use.
Okay, I use radiography for surface qualification of alpha surface. You know, we have to prepare alpha surface as a surface. And then when you use the position of sample right? That time alpha activity is not
Yeah, of course. The electron position, usually it is on the edge.
Yeah.
And in the center is
Nothing.
empty.
Yeah. And then
Yeah. You
know,
can use the radiography to review this picture.
yeah. But I didn't use soil that asking how can you prepare with that soil sample. You know, if you have that more big you can cut it. You can cut it. Thank you very much. And then can you calculate
Radiography. If you use alpha track, solid state with the detector, and with what alpha track picture, it is very simple to calculate. You can measure the the number of alpha tracks, you know the time, you know that all the alpha tracks go to only 2p geometry.
Okay.
So, and you know the effectivity of your detector, because the surface is etched and some part of information is lost. If you use standards, you can measure this effectivity. It is not a problem. But for imaging plate, if you don't know the radionuclides, you have only some black spots. And the intensity is different. Using image J, you know this problem. Software for working with images. It is free, very good software. Image J.
Image J.
Image
Can you
J.
write?
Yeah, I can write if I can. Software for it is good.
Okay.
And you can make 3D picture. Here it is your surface, maybe some spots, and it could build you and you can separate alpha and beta.
Yeah.
And this is that it is intensity of digital luminescence. In some machine use PCL, it means photostimulated luminescence. This is different units, but the same results. So you can compare your particles.
Okay.
So this is beta, usually this is alpha.
Okay.
The shape could be different. It is free software.
Free software.
And
Okay.
there are very big amount of different applications in it.
Okay.
A lot of users. It is very good.
Okay. Thank you very much.
Very good software.
Thank you.
Not at all.
Just a bit, especially on YouTube.
Acceleration analysis.
Do we have a team?
Unfortunately, we have not made any reaction in Moscow. Sometimes it was reactor because it must be close to the laboratory. Now all the reactors from Moscow, because it is
So we need a reactor for this.
of course, neutron analysis without reactor you cannot make. You cannot.
So what are the fundamental principles?
Fundamental principles. You've got a sample. You are to put it into the reactor. You are to know the fluids of thermal neutrons. You know the different nuclear reactions which could be in your sample. And after that, you measure short-living nuclides, which are the results of these reactions. You know, different reactions like and some else, and we've got manganese and some radionuclide isotopes of manganese, which could be analyzed using gamma spectroscopy. So thermal neutrons is the first. You are to have a reactor, which is a problem. If you work in the nuclear center and you got a reactor close, yeah, and then you have all the table, all the periodic tables.
This method even analysis or
Simultaneously different elements. Yeah. Yeah. But you cannot do anything about reactor, the research reactor. This is a problem. For many years we've got reactor, Nishi Institute.
Why is the main reason why you commission this representative?
Because in Moscow, it's megapolis. It is our safety regulators told us that it is impossible. So many people. It is a great risk when research there. So they are far from Moscow, and it is not convenient because short living. Short living.
Yeah, thank you very much. Shall I take a picture of this one? Yeah.
Oh, of course, of course. Oh. Thank you.
Вы будете им отдавать эти предметы?
Да, они некоторые просят. Значит, смотри, ты узнал?
Я хочу, не хочу ППТ им отдавать. Если будете отдавать, то
PDF, да. Ты можешь его скопировать?
я копирую оба, потом.
Да. А выдаем мы им А выдаем мы им тогда. Слушай, ну если вы не свои вопросы,
Да. А здесь еще зум какой-то?
да.
То есть что-то еще там?
Там трансляция.
Ну это Спасибо. Понятно.
Все кухни
Ну что, лучше стало как-то? Ну, это не советую. Какие-то стрёмные люди. Во-первых, можно говорить то, что нужно сделать еще завтра. Часто бывает не так, знаешь?
Выразить подпоры, потому что просто не просто прямо вообще очень почему хотел с этим посетить сделать.
Ну, если они сами не придут. А слушай, до скольки? До 12:45, правильно?
Ну да, если там будет раньше, то
Они потом идут?
Да.
Может быть, это чуть пораньше, конечно. Я не люблю медленно говорить. А ты знаешь, может быть, да. Потому что у меня вообще кашля. Но у меня все нормально. Проблем. Okay, I think we can start because it's time. Starting. Good morning, everyone. I'm happy to see you here, and today I will give some lecture about the process to be considered in modeling of the radionuclides migration. I actually didn't know about your background, and I hope that everything will be clear for you. But if not, you can ask a question to me, or maybe you can stop me and say that you know everything that I'm talking about. It's no problem. And today I will try to show you the way how we can try to model radionuclide migration in the environmental. And we are right now in the radiochemistry division. That's why, and I'm also radiochemist. That's why I will show you maybe mostly chemical ways because I'm chemist. Okay, let's start. When we're talking about radionuclide migration, of course, the main question is why we need to understand the migration of radionuclides in the environment. And of course, most of us well know that there are a lot of accidents, there are a lot of there are a lot of nuclear events which goes to radionuclides entrance to the environment. And after that, some of the territory are highly contaminated. And for today, we have a lot of areas which are contaminated by radionuclides. And this territory needs decontamination, of course. But from our point of view, in all countries for working with nuclear energy, today we need to build nuclear waste disposal. And to create a safe nuclear waste disposal, we need to understand how radionuclides may leak from the nuclear waste disposal and how then they will be break in the environment. Therefore, a lot of scientists and engineers try to understand the migration route in the environment to make it more understandable and then to prevent it. Okay, if you're talking about chemistry, behind the what?
Can you speak louder?
Louder, okay.
Or you can use the microphone.
If you want, I can use a microphone, of course. But I don't know how it's working. It's usually with some devices. It's better now?
It's not necessary. This battery is DC battery, so you can directly use it. Make it
Now it's better? Yeah?
Yeah.
Okay, okay, very good. Now it's okay, yeah? Okay, perfect. Okay, when you're talking about chemistry behind the radionuclide migration, we need to emphasize 4 types of the main reactions which control the behavior of radionuclides. First one is social reaction because it's quite important in the context of radionuclides and actually not only radionuclides but any heavy metals migration in the environment. Second one is complexation with different ligands, I mean inorganic and inorganic ligands. Third one is redox reactions, especially in context of actinides migration and the solubility reaction and formation of insoluble phases. When we're talking about complexation with ligands, we can divide this area on also another subtitles. First of all is hydrolysis reaction. It means that interaction of cations with water and following hydrolysis. Second one is interaction with inorganic ligands. Third one is complexation with natural organic matters. And third one, interaction with bacteria. Because
during the modeling, we need to have both mathematics and chemistry. And the main law which we can use during modeling of chemistry behavior is mass law equation. What means when we can write the chemical reaction. It's a simple way how we can write the chemical reaction, where we have precursors on the one hand of the equation and products on the other way, on the other side of the equation. And then we can write the equation for the constant, equilibrium constant, is K. And on the upper part, we have activity of the products of the reaction, and the lower part, we have a activity of the precursors of the reaction. This mathematical expression is the main expression for the whole modeling of chemistry, and actually in laboratory system, and of course in the environmental system as well. When we're talking about stability constant in thermodynamics, in classical thermodynamics, we usually operate it with equilibrium and standard, with the equilibrium constant in standard condition, where we have expressions with concentration and activity. In case of usual, mostly more popular expression, we can have stability constant in the expression of by concentration, concentration-based equilibrium constant. Where it is quite important, it's quite important in high salinity solution, or it means that it's, for example, salt disposal or groundwater where salinity is also high. In this special cases, you should be very careful when you're talking about modeling, and you need to have a big difference between equilibrium constant and concentration-based equilibrium constant, because activity is not equal, is available in that cases. But in pure solution, in solution with ionic strength lower than 0.1, we can actually not have a big attention to the activity coefficient. Okay, if we want to go to the actinides, because my lecture is mostly about actinide behavior, you can see that for different actinides, different oxidation state is more stable. You can see that in bold we distinguish the more stable oxidation state for the different actinides. And as you can see that for different actinides, this oxidation state is different. For example, for uranium, it's the most stable oxidation state is +6. For example, for actinium is +3, and yeah, of course it's different. And the different oxidation state means different properties. Different oxidation state results in different ionic structure. What does this mean? When we're talking about 3-valent actinides, the typical ion is actinide 3+. When we're talking about with formal charge +3 and effective charge +3 as well. When we're talking about tetravalent actinides, the charge is +4 and the ionic change actinide 4+, and effective charge is again +4. It's easier. But however, when we go to the pentavalent and hexavalent actinides, they usually perform in the form of oxycations, actinate O2+ and actinate O2 2+. And in this case, the formal charge is +1 and +2 respectively, and effective charge +2.2 and +3.2. Why I emphasize this for you? Because it's have a highly influence on the chemical properties of these cations. As you can see, the role that increasing complexing affinity is following. Actually, complexing affinity is proportionate with effective charge, as you see in this row. What this means that if we have neptunium, which is usually 5+ and present, and neptunium cation with the formal charge +1, neptunium cation is highly non-reactive active. I mean that it means that in usual solution, neptunium is usually like neptunium O2+ and do not want to react with anything else except the water. However, actinide with high charge like plutonium 4+ or americium 3+, they can interact with everything that you have in the system, like bacteria, like organics, like minerals, like water, and everything you have in solution. And when you are talking about, therefore, we cannot say something general like radionuclide behavior, because each radionuclide will have a special chemical properties and will have a special migration behavior.
So does it mean actinide oxide is more unstable compared to AN4+?
It means that dioxycations is less activity, have a less activity to reaction, and it should be more mobile in solution, actually, usually. It means that if you have, for example, neptunium, neptunium will not react with most of the solvents, most of the bacteria, and something else. It will stay just neptunium in solution, and will go with your solution if your solution goes somewhere. For example, if you have a pond, in the pond, neptunium will be in solution, and for example, americium and plutonium will go to the bottom and react with the mineral on the bottom. If you have a direction flow, neptunium will go with solution with flow, and the americium and plutonium will solve on some minerals and stay for some, at least for some time.
So they are less interactive.
Yeah, neptunium is less interactive because have a lower charge, and the americium and plutonium is more interactive because of a high charge. Just physics actually behind this chemistry.
So it's electron affinity.
Yeah.
Electron affinity and negative.
Yeah. And here's the hydrolysis. Yeah, it's like the similar thing that we discussed right now. Actinide 4, it means that actinide who usually presents in tetravalent form, they begin to hydrolyze really low acidic pH. However, for example, pentavalent, they have start to hydrolyze on the high pH. You see that. For example, plutonium 5, pentavalent, it didn't hydrolyze in all pH before 9. Yes. However, plutonium 4 is hydrolyzed at very low pH and different from a present in solution. And here is a general expression of hydrolysis reaction. It's again similar with the general expression with all chemical reaction, but here we have a special case with for hydrolysis when water reacts with cations. And here is the stability constant, for example, for this hydrolysis reaction. And if you sometime you will start to modeling chemical reaction, I don't know, for some reason, you need to be careful and check to the constant and reaction. For example, you see these two reactions is very similar. However, expression for the constant will be different. You see that here is water inside the reaction, here is OH minus. Is two way of writing the reaction. However, the values of the constant will be of course different, and you need to be careful during this and not to change the value of the constant. Okay. When we're talking about actinide complexation with halide, we can again actually with halide, actinide complexation with halide is sometimes important, especially in high salinity solution. However, in most of the solution, when you're talking about just environmental water, halide is not so important as other oxy-containing anions. And there is a general trend for the different inorganic anions, and as you can see that hydrolysis and the OH anions and the carbonate anions the most important in context of environmental migration, and also sulfate and phosphate anions may be sometimes very important in context of migration. And again, we can write the reaction describing interaction of actinides with the particular ligand, and write the, and if you have the constant for this reaction, you can model it, and you can calculate how much part of your radionuclides will be complexated, and which part of this cation will be free.
Excuse me.
Mm-hmm.
The plot is logarithm, right?
Yeah, it's logarithm of constant value.
How the values are 5, 10, 15? How the values are 5, 10, 15?
Minus?
No, it's a logarithm scale, right?
Yeah.
So how the numbers are like this?
It's the value of the constant. It's a really typical value for the constant. It's maybe from -20 to +20. It's okay for the constant.
Okay. So
If you have a very high value of the constant, it means the reaction promotes is very good.
okay, so it's
It means that your
bigger value, then make the logarithm.
Yeah.
of that.
yeah. Here's the example of uranyl carbonate speciation, and actually I think that for the environmental uranyl carbonate speciation is very important, because in the most of the system where you have a carbonate, and you have a carbonate like almost everywhere in the earth, uranyl will complexate with carbonate and form different species which will affect on the chemistry of uranyl interaction. Actually, complexation with carbonate is highly important, not only for uranyl, it's also quite important for strontium, for neptunium-5, and for plutonium at 5 oxidation state 5 and 6. Natural tuning ingots, actually it's really difficult topics, natural organic matters, because it's quite different. And if you're talking about inorganic ligands like carbonate or H or chloride, it's much more easier compared to the natural organic matters, because it's really diverse. But I need to give you some really general terminology. Maybe it will be help you in future. In natural organic matter, we can divide it to dissolved organic matter. It means that organic matter which can be flow with water, and we can also divide it as natural organic matter to aliphatic organics, to amino acids, and saccharide. All of these can present in natural system because of organic material generated as exudates by organisms and plants. And of course, it's present in ponds and rivers and soils and so on. Second important things in case of natural organic ligands, it's siderophores. Actually, in the literature in the last 10 years, it was observed that siderophores have a great importance in case of plutonium migration, because plutonium can take place iron-3, which is quite important for siderophores activity. And this type of migration is quite important for plutonium and maybe also for uranium. If you have a place where you, for example, your environmental condition is quite good for siderophore activity, you need to account this possible reaction and this possible way for the migration of actinide. Humic substances, it's again, it's kind of natural organic matters. Again, some dividing to make the system easier. We can emphasize humic acid, which are soluble above pH 2, fulvic acid, which is soluble in all pH values, and humin, which is soluble fraction, it's like solid mineral. And actually, humic acid substances is quite different because they have a lot of different functional groups, and they have different redox activity, and they have not really stable structure. Again, compared to carbonate or chloride, if you have a chloride or carbonate, you know the composition of your system. In case of humic substances, you don't know exact composition. Any humic substances are a little bit different from each other. Therefore, in the literature right now, we have some complex constant, of course, but it's like general assumption, not in particular case, your humic acid may be a little bit different from general humic acid in humic acid society.
Excuse me.
Mm-hmm.
I don't have chemistry background, so
Okay, no problem.
please don't take me.
Yeah.
How pH value plays a role in the whole scenario?
And pH value is very important for whole scenario because pH is controls most of the reaction. It controls conversation reaction, it controls sorption reaction, it controls solubility reaction, and of course it controls transport properties.
I mean, pH doesn't influence anion or cation. It doesn't increase the electric charges. So how it plays a role in?
It's changed.
For example, pH if I lower or increase, my 2 plus cannot be 4 plus or cannot be 2 minus. So how can it combine with the host?
If you have a reaction where H plus is alpha participant, it's easy. For example, if you have an acid solution, you have a lot of H plus in the product, it means the reaction will go to the precursor. And again, if you have a S-base condition, you have a more promotion to the product.
So it directly influence the beta factor.
Yeah. And again, you need to remember that pH is minus log.
Its concentration.
Yeah. If pH 0, it's minus log, its concentration is 1 molar.
Yeah.
And if it's pH 12, it's 0.0000.
Got it.
Then we go small overview of redox reaction. Redox reaction, again, is quite important because, for example, if you go to the plutonium, it's my favorite element, and you will see that we have a lot of oxidation state, and you need to understand that plutonium 3 plus or plutonium 4 plus, it's not the same as plutonium 5 plus and 6 plus, because 6 plus and 5 plus is plutonium cations with different chemical properties. Therefore, the changes between the oxidation state will change chemistry behind this element totally. For example, by using alpha spectrometry or gamma spectrometry, you can measure that you have plutonium inside your soil. But you didn't understand it's plutonium 4, plutonium 3, plutonium 5, or plutonium 6. You don't know chemistry behind it. And then you need to understand which film of plutonium you have in your soil. It is more complicated task than just measurement in becquerel. Okay.
It will be always in compound form.
Huh?
It will be always in a compound form. Compound, not in pure plutonium.
Yeah. So, but even in compound, it may be 3 plus plutonium or it may be 6 plus plutonium. It's for example, you can have solid carbonate or you have solid phosphate. Yeah. And I need to say that for other actinides, the redox behavior is slightly important. I need to emphasize on uranium because uranium have also a lot of oxidation state, and environment we can find uranium 4 plus in underground condition mostly and in reducing condition, and uranium 6 in oxidizing condition. Neptunium as well have a redox transition, but it's not so important again. But for plutonium, it's really important. And there is again the chemistry behind the plutonium. Here you can Nernst equation, Nernst diagrams, where we can see that potential between transition of plutonium between different oxidation states. And you can see that for transition plutonium-6 to plutonium-5, you need 1 volt. For transition plutonium-5 to plutonium-4, you need almost 1 volt. For transition plutonium-4 to plutonium-3, you have again 1 volt. And for transition plutonium-6 to plutonium-4, again 1 volt. What does this mean? That you don't have any quite favorite oxidation state. The transition is very easy to each of them oxidation state. And what we have in the result that for plutonium, we sometimes have 4 oxidation states in one solution. Sometimes it happens, and it's not really difficult situation for plutonium. And plutonium can easily change oxidation state between each other. And this is the most complex part in the case of plutonium chemistry. And even today, we didn't understand how we can easily calculate it, or how we can make the expression for plutonium chemistry. And I need to say that modeling of plutonium is the most complex part today for the all radiochemistry or engineering, unfortunately. And we can look to the prоб diagram. What this means that we have pH on the one axis and EH value for the other axis, and we can see which oxidation state is more favorable in this condition. I need to emphasize that it's more favorable oxidation state, not means that it's only one oxidation state, but it's more favorable. And you can see that in the underground condition, plutonium is mostly stable as plutonium-4 and some plutonium-3, and in oxy conditions, sometimes it's mostly present as plutonium-5. However, for this prоб diagram can change when you add some reagents to your system. What means reagents? It means that if you add, I don't know, siderophores, diagram prоб will change. If you add chlorine, diagram prоб diagram will change. And it's even here you can see that it's prоб diagram with carbonate, and if you just take out carbonate, it will be changed as well. And therefore, for your system, if you want to model your environmental system, you need to know at least the most important components in your system, which can affect the migration of your radionuclides. Now we go to the sorption reaction. Sorption reaction, it's in general what this means that it's your soluble cations or anions interact with insoluble solid phase. Mostly it's inorganic minerals, and it may stay on this surface and not migrate to other places, or it may be also some colloids which can be also transported with water. In the overall list of the inorganic minerals which are possible in the environmental, the most important in context of actinides migration is iron oxide, because they're highly active to the most of the actinides. Clay mineral, because it's also good absorbents. Quartz is not as good as sorbent, however, it's everywhere. And sometimes the accessory minerals such as manganese, titanium oxide is also quite important because they have a high sorption activity to the actinides. How we can model sorption, or how we can mathematically predict the radionuclide sorption? There is two ways historically that was used for describing sorption of radionuclides. First is KD approach, is very old and maybe the most easiest, but Okay, speedy approach. What this means that in the laboratory you can experimentally determine the PD value for the particular system and then use it to the modeling. It's quite simple, as I said. However, this have a big limitation that you cannot change the condition in your system. For example, if you have PD value for exact solution in the exact solid phase, you cannot predict how my system will change when I change the pH value, or how it will be changed when I add some, I don't know, citrate to the system or siderophore to the system. You cannot calculate this option with changes of some parameters. You need to do another experiment and have another KD value. Another approach is surface complexation modeling that is quite popular today, and I hope it will be real as a result. In case of surface complexation modeling, we need to, as we did with aqueous complexation, we need to write the reaction, we need to find the constant and write it to the modeling of the system. It's a little bit more complex in experimentally, but in fact, this modeling will work with a wide range of conditions. You can make prediction with changes of pH or concentration of your ligands or concentration of your solids or concentration of your radionuclides. You can, this system will be more have predictability. How it looks like, actually, it's again, after hydrolysis or after complexation reaction, it looks the same way. You need to write the equation. It's quite similar. You have your cations, I mean, your radionuclides, and the surface. This is how we write it down. When we're talking about, I don't know, iron oxide, for example, we assume that on the surface of iron oxide we have functional groups, and our cations interact with these functional groups, and these surface complexation species are formed as a result. Again, it's the same with anions, it can absorb as well. The difference between the equation in the first part of my talk is only this. This part, which means that Coulombic interaction, because you have a plane with charges and you have a point charge. When your point charge go to the plane with other charges, it's Coulombic interaction. And this Coulombic interaction you will write down to the additional expression in your mass law expression. Theoretically, it's really easy, and it's the same way as you use in solution. However, you just add this Coulombic interaction term.
So in this whole exponential function, there is no distance. If we use Coulomb's law, we need a distance.
They use the potential.
So okay, we have the electron potential.
How it works in experimentally, for example, you have a pH H for the sorption of, I think it's americium onto both side. You have a good experiment, and then you can fit it and determine the value of your log KD. There is a list of some very useful and famous programs, software which are used right now for this process, for the modeling of sorption. And I really need to emphasize PRIXI program. The PRIXI program, it's American program, but it's open access, and it's, I think, the most famous in context of radionuclides or any cations migration in the environment. What is the big part of this surface compensation modeling that we don't know exact equation of this sorption reaction. We can only assume it. We don't have any direct spectroscopic or micromicroscopic methods to determine the exact equation of this sorption reaction. Therefore, some other groups or some other scientists or some other engineer can use different stoichiometry of this reaction, the intensity and sorption site type. And there is still a variety of literature, and still there is no only one opinion for this sorption reaction description, but I hope that maybe, I don't know, during some times, all the world will have only one decision. What we can also do, if you have, for example, number of your radionuclides and you have a number of sorption data, you can also plot generalize your data. For example, here you see that it's linear free energy relationship between hydrolysis constant and constant of sorption. You see that the data have a pretty well correlation between hydrolysis and sorption reaction because they have actually similar equation. The equation of sorption is really similar to the equation of hydrolysis. Therefore, we can assume that it maybe have a similar mechanism and it should have similar constant, or it will correlate each other. And for today, you can go to the different databases. I advise you to maybe look to the Rosendorf databases. It's open for everybody. You can just use the website and found this. You can just write this down, yeah, and then you can find the minerals. You can choose the ligand, and they have actinides. They have some other cations. And for example, here I choose nictonyl and choose goethite, and you see the list of the available data from different papers. And you see that different papers have different reactions for the describing nictonyl sorption onto goethite. Some of them is quite similar to each other, some of them is quite different. And there is one problem that for today there are different opinions, different scientists describe the sorption by different way. But anyway, I think that it should work in much better than just 3D approach. Okay, and then when we go to closer to nature, you don't have any pure minerals in your system. I mean that you don't have a pure goethite in your pond or in your river. Usually you have a complex mineral assemblies, yeah, or complex system. And the ideal way, if you have different minerals inside your complex system, you need to understand how much different minerals you have in your system, and then calculate sorption on each of them, and put it to the big equation, and try to model it. It will be perfectly works. However, because it's too complex, there is another way that can help to save the time. You can just find the dominating components. It means that components which will dominate the behavior of particular radionuclides in the system, and write sorption reaction only for them, and not account, for example, sorption onto quartz because it's too low in context of this interaction.
So how much accuracy you lose then?
It again depends on your system.
Depend on the system.
Yeah. The next part is solubility reaction, and here you can see the solubility of hydrolysis species. I mean that hydroxide of general trend for hydroxide solubility. And again, as you can see, the actinides 4+ have a lower solubility because they have a higher affinity to the reaction. The solubility is quite low. And pentavalent actinides, it's again, they have a higher solubility and higher possible concentration in solution. For some scientists or some, I don't know, model, actually solubility is the conservative way to predict the actinide concentration in solution. Because solubility curve is the maximum of concentration of particular actinide in solution. If you have this profile and if you know that neptunium in your system is pentavalent, you know that concentration of neptunium will not be higher than this curve. It cannot exceed this curve because if the concentration of neptunium is higher than this curve, neptunium hydroxide will precipitate before this concentration level. Did you got the idea? Yeah? Therefore, here is the maximum possible concentration. And of course, if you know the concentration, you can estimate the possible maximum becquerel. If you know the maximum concentration of neptunium is 10 to the minus 5, you can understand which maximum of becquerels you can possibly have in your system. Maximum, it's because it's conservative calculation. And then you know that if neptunium 5 will be maybe a little bit sort on the bottom sediments, you can see that its concentration neptunium will be even lower than 10 to the minus 5, and you can calculate how much lower it can be as a result of sorption, for example, reaction. For example, our German colleagues in KIT is quite interesting to the solubility studies, and they use the solubility study as a conservative prediction for actinide concentration in solution in the nuclear waste disposal. And here is again the open source, and I really like it, and I advise you to again go to this website. What is it's a NEA database, nuclear energy agency. Yeah. What they have, they collect the databases for all thermodynamic constants. For example, they have books for uranium, americium, technetium, thorium, and they have updates for uranium, plutonium. And this year, 2021, they have published again update for the actinide chemistry. And it's quite useful because what they did, for example, we can, for example, if you are interested in hydrolysis reaction, hydrolysis of uranium, you can read this book and you will find how many papers about uranium hydrolysis is published, and they do critical review of all of these papers, and sometimes they recalculate data, and sometimes they did not advise you to use this value of constant, or finally they write it down that the most trustable values is following. And it's for some reactions they write that data is still not sufficient, and you need to be very careful if you use this particular value. Therefore, if you sometimes will model your particular speciation of the radionuclides, you definitely need to go to these databases and choose the constant, or at least read is it good or not. Unfortunately, the sorption project of NEA was closed. They started it, and the plans to do the same books for the sorption reaction. However, because of this non-agree between different scientists, the sorption project was closed, and I think they may be open later on when the data or understanding of the sorption system will be more deep than for today. Okay, summarizing them, it's what I can to say that if you have some very complex natural system, you need to understand which reaction is the most important in your case and try to model it each of them and try to find the constant for each of them and try to estimate how your particular radionuclide will work in this system. What I need to say for you that, of course, I think that after, I don't know, maybe 10, maybe 20 years, we will have a lot of data for all of this reaction, and maybe we'll have a very smart computer with machine learning and so on and so on, and where we can just put on the one button and it will go, say to us which reaction will take place in your system and on environmental system. But today, of course, it's not work so perfectly. And for each system, for each places, we need to first understand which reaction is more important. And because of the natural system is quite complex, and you should understand that it's quite difficult to compare, I don't know, Siberia forest and tropic in the US. It's not the same actually, yeah. And of course, the chemistry and mineralogy and water flow is quite different. Therefore, if you have some special system, you need to understand your particular system first, and then just provide general equation for everything. Okay, and then it was the chemical part, but again, you need to understand that chemistry is not the same as the all of complexity in the system. What is the most, again, most popular and the most important today is the reactive transport modeling, which is combining transport modeling and chemical reaction modeling. And here we have a chemist and we have a hydrogeologist, yeah. Hydrogeologist can write the equation for the flow, and then we can flow of the water in your porous media, and we can just divide it to our porous media to the small pieces and write a chemical reaction for each of them. And then we can calculate how our radionuclides moved or not moved, or maybe stay on one place. And this is this may help us modeling to the large scale, to the long period of time, and it's still challenging for today. In the last part of my presentation, I will show you some, there's no theory anymore, and I will show a little bit part of the examples from the actual samples, where you can see that there is different mechanism control radionuclide migration. First of all, I will show you my favorite example. Actually, it's from USA, not from Russia. Unfortunately, no, but it's a very good example where science helped for the remediation, and where you can see that science is not only boring thing, but it's also very helpful for at least even for money. Okay, there is Rocky Flats. Maybe you know that Rocky Flats was a plant where plutonium for weapons was made in USA. And it was, DOE was choose the strategy for the remediation of Rocky Flats. First of all, they determined the plutonium concentration on the territory, and as you can see, there is some hot spots. I mean, some of the territory is highly contaminated with plutonium because of fire accident, and some of them is not so contaminated. And firstly, DOE estimated for remediation they need $37 billion and 70 years, because they plan to put all soil from this Rocky Flats to the special machine and wash it with reagents, and then wash it again, and then wash it, and then place on the same place. And they invited scientists to understand in which plutonium oxidation state we have in this particular soil. And they used the synchrotron-based techniques and found that in some hot spots, where fire was done, plutonium presents as plutonium-O2 particles. It means that it's highly insoluble oxide, and if you will try to wash this soil by any reagents, you didn't have any good results. Because solubility of plutonium-O2 is too low. Maybe you remember I showed you diagram, and there is no meaning to do this washing for these hot spots. And finally, the plants was changed, and as you see, radionuclides was totally remediated, and the price of this work was decreased to the $7 million. And time was in 2006. It was finished, and right now you see that we have a green grass on this territory. It's a good example, and I hope that we will have a lot of examples from any countries, not only from USA. Another example, but not for remediation, it's again from USA. It's one of the most famous scientific paper about plutonium migration from Nevada. Nevada is a place where a lot of nuclear weapons tests was done in the US. And what scientists have found that, again, previously it was thought that plutonium will not migrate far from the nuclear weapons testing, and will stay in the same place. However, any person with colleagues found that plutonium migrates up to 4 kilometers from nuclear waste nuclear testing, and it was found that was migrate with clay colloid particles, and from this time the studies about colloid migration of radionuclides were started. Maybe Irina was talking about it, no? What I need to say right now is that after, it was 1999, and today in 2020 they published another papers, and they still working about this, and they found that actually this clay and the light particles which were taking plutonium from the nuclear testing place was formed not as a result of plutonium absorption onto clay. They was formed because melting glass alteration. After nuclear testing, underground nuclear testing, local zone is transforming to glass, and this glass, after interaction with water, can alterate and perform some clay and light particles which migrate with water down from the local nuclear testing place to environment. Therefore, this colloid particle with plutonium was go to some groundwater system in the test site. Another example is from Russia. Here we again have plants where plutonium was produced for the first nuclear weapons project. And of course, I need to say that radioactivity, working with radioactive materials in 1950s was much worse than for today, of course, and what they did in that time is not possible for today, hopefully. But what was done, because of the lot of liquid waste was produced, they put the nuclear waste to the open system of Techa River. You can see that from 1949 to 1941, more than, I don't know, huge amount of radioactive waste was disposed to Techa River. And as you can see that firstly, the Techa River was really highly contaminated. Then they produced the Techa cascade of the reservoirs, make some ponds to preserve radionuclides inside them and not move and not let them move to open system. also create some additional channels for the river flow. It was pure, and finally you see that for today we have a lot of system for the open source water, and they of course still contaminated. From 1951, they stopped dispose the nuclear waste to the open system and disposed them to the closed pond B9 or Karachay Lake mostly, and B17 or Old Swamp Lake. And you see not right now, it's a photo of these lakes, and the most famous from Russia, the most famous radioactive waste contaminated place in Russia is Lake Karachay. As you can see that in this lake, a huge amount of activity was wasted. However, volume was really small. And for today, this lake is totally closed. It means that now they stopped dispose of radioactive waste to this lake, and they put this cover to this lake. But work was done that our head these co-workers check the migration of plutonium to the wells around this lake. And they was found that plutonium migrate with colloids again. You see that this concentration is quite different for different distance, but you see that it's even for the 4 kilometers distance, they will found plutonium, and this plutonium was together with iron manganese colloids. You see that in Nevada, we have plutonium with clay colloid. Here we have plutonium with iron manganese colloids. There is again shown to us there is no only one way for example, plutonium migration, different geochemistry, different conditions. Here is disposing of radionuclides to the pond. In Nevada, it was nuclear testing, and of course the final migration form is not the same. Yeah, because of not only the type of the salt, because of dispose composition as well. Because it's liquid solution go to with iron inside the solution go to the pond with high pH, and iron perform precipitates like perihydrite, goethite, and so on and so on. And these colloids may move with to the groundwater. Yep.
So that was not clear for me in the first part of the lessons, slide number 15, where you saw that plutonium. If we take for example, a cross section of a mine, on the surface is oxidized and the below is reduced.
Yeah.
So, but plutonium doesn't occur natively on the surface. It is in the uranite form. Uranite is the host ore of the people.
Yeah,
so it is not available freely or natively.
It's not the case of plutonium because of the redox reaction. During the reaction, plutonium is iron oxide, so manganese is reduced to plutonium swap.
You also saw the picture carbonates also is combined, or silicates. Silicates is not so dominant, but ferrous. Ferromagnesium minerals are in the host rock. So how can we really quantify the amount of plutonium on the whole area? It's not a ore. If it is a ore,
yeah, like of course it's not the ore.
If it is ore like uranite, we have a method, geophysical method to quantify the amount of the ore or the area, how much volume and total amount. But plutonium is like a soil particle, so it's mixed with also another degraded particles, minerals on the surface. So how to quantify the amount? Like Nevada sites, Nevada also their University of Modelirada mines.
Yeah.
They deal with that, what you saw the pictures.
Mhm.
But that is not no publication about that. How much amount of plutonium were reprocessed and
Mhm.
then replaced?
Yeah, yeah, because it's really difficult. It's not really easy to answer on your question. And in case of plutonium, as I said before, it's much more difficult than, for example, for uranium. And even in this case, they found uranium as well. And uranium, as we say, see that uranium is present in soluble form because it's carbonate complexation. Uranium moves just to uranium carbonate complexes. But in case of plutonium, it's much more difficult because
It can mix with anything.
yeah, and but of course, in both of the cases, in case of Nevada and in case of Karachay, plutonium that was migrated from the source is like, I don't know, 0.00001% of all plutonium that was located in the Karachay. I mean that migrates only small part of the plutonium. However, because we have a very low limit of possible concentration of plutonium in the drinking water, yeah, its equal level is 0.55 becquerel per liter. Possible concentration of plutonium in the water is 10 to the minus 12 mole per liter is possible concentration of plutonium in water. And of course, this concentration and exceeds this level of possibility, yeah. And yeah, it's still very difficult to predict it. And first of all, what we did right now for plutonium, we tried to understand the possible ways how it will migrate and with which particles or with which substances and which reaction is important. And then we try to calculate it by mathematics. It's of course it's a long way and complex way, but we are working, and not only we, yeah, and of course all scientists try to calculate. And if you look at the scientific papers, you see that for some cases it's good examples. For some cases, there's still just the fact that we have plutonium migrate, not the calculation, not estimation. Just we see.
So normally plutonium is in a cluster deposit. It's a type of deposit or cluster deposit in. So it depends on how much distance is migrated from the source and what was the carrier. It was carried by the winds or the normal biological agents or river and which directions. So these parameters has because the higher it migrates, degrade its plutonium radioactivity impact on the soil or on the ground. So these parameters is really difficult to quantify.
Yeah, it's true. It's difficult to quantify, but we try to do it. And right now we just try to understand the most important reaction, and then we try to put it to the modeling. And I hope it will work for some time. And what I need to say that again, the most important problem that, for example, you know the wall reaction, you maybe know how 99.9% of plutonium are present in your system, but you still have 0.01% of plutonium which have been other form and may migrate to somewhere else and participate in other reaction, and it will, of course, influence on your becquerel in some way. And of course, all radionuclides try to migrate from the source of contamination, and of course, it's still a big problem for the engineering and for the future, which will be solved, especially in the open systems like lakes or like ponds or like nuclear waste tanks in Hanford site where they lead to the underground soil and still can migrate down to the groundwater table.
I mean, this parameterization, source of formation, source of contamination, in between whole parameterization.
Yeah.
That's the real challenge for the model.
Yeah. And from my point of view, to determine the expression between, for example, how much plutonium you have in the source and when it will be goes down, and how much you need to understand your system. You need to try to understand which reaction control you. It's phosphate formation, or it's absorption with iron colloids, or it's, I don't know, oxidizing, or it's reducing, or what. And then you try to estimate firstly, and then you make your estimations better and better with time, with your understanding of the system. And last 5 minutes, I'll show you another example. It's seawater. It's quite different from the pond and the nuclear waste testing. Maybe you know that in UK they have a similar nuclear complex, and they discharge plutonium in big amount to the seawater. And what they have as a result, the plutonium have in seawater around the solar field. And what is interesting, that is, again, it's very understandable from the chemical point of view, the plutonium which not bound to the particles is plutonium-5 in solution, plutonium-5 or plutonium-6. And because it's not active chemical species. And plutonium which was bound with some colloidal particles is plutonium-3 and plutonium-5, not plutonium-4. And what is, from my point of view, what is even more interesting, that some of the guys was compare profile of plutonium distribution from the depths in different sea, around the world, and the profile is quite similar to everywhere. And the maximum of plutonium was in the maximum on the some depths where a lot of colloidal particles was located. I don't know, for me sea is not really close topics, but for everybody who understands the sea behavior, they understand that on the some depths there are a lot of particles, and where fish eating some of them with plankton and zooplankton, phytoplankton, and so on and so on. And in this region we have a lot of plutonium because it's bonded to these particles. And in other places, only soluble plutonium mostly present, and this soluble plutonium will be plutonium-5, plutonium-6. And here you see that it's similar profile. For example, for seawater, it's easy to predict the behavior, at least for even other places, compared to, for example, ponds, because they're different in the chemical composition. Another example from Chernobyl, and I will not put the detail for all the Chernobyl, but what is interesting for me was is a red forest, and there was place where during the decontamination of red forest, all of the trees and all of the green grass or some vegetation was put into the trash and was placing for some years. And after that, scientists will measure plutonium outside this trash and found that plutonium migrates to the distance more than 10 meters. And in this particular case, plutonium was connecting with natural organic matters, because we have a lot of organics inside the trash. They degrade sometimes, they're humics, natural organic matters. Again, there's bacteria and so on and so on. And in this particular case, there is no inorganic colloids which were moving plutonium. Plutonium was moving with organic matters, because in this particular system, organics was dominating the behavior of plutonium. And you see that in different systems, you can at least try to understand which way of migration of my radionuclides or my radionuclides of interest will be dominating, and then maybe you will try to calculate it by mathematics using the KD or constant and so on, reactive transport modeling, and then maybe you will be successful with the migration of radionuclides in particular place and particular migration zone. Okay, I think I need to finish, and yeah, my home message for you that for today we try to understand both. We analyze environmental samples from actual radioactive radioactive contaminated zone and try to understand their behavior. And from other hands, we do lab experiments to find constant of reaction. We try to modulate it, and then of course we will do reactive transfer, combining both real experiment and lab experiment. Okay. Thank you for your attention. And maybe one more question. No? Question?
So let's take a lunch.
What are you working with radiochemistry lab?
Yeah.
In this,
I'm looking at mostly on this plutonium and interaction with minerals.
you are a professor or researcher or scientist? Okay, so can I'm interested to work in this group. It's mostly especially in a real world scenario problem for politics. So if you
What do you mean real world scenarios?
I mean, it's not projects, not academic, but research projects. Any project related to
You mean
research?
for the research?
Yes. Any. So for research, really good to have some backgrounds, and I want to learn by doing. So be useful at the same time be productive.
And where is it open?
My field was related to completely different industry. I'm working in for mass
In
mixing.
the Moscow.
Mass mixing construction. So it's completely different. But I have background mining and yes, and planning and then monitoring. So I really one concept is that I want to use the knowledge at the same time long to be towards the mostly can we have a meeting?
Anyway, I need to ask Vladimir because I don't really understand about the direction of the Saturn.
So you are only dealing with your second subjects.
If you mean the field one, it's a processor.
Nothing from non-second subjects.
What does it mean you don't
Department of Science and Technology, the Ministry of Science funding.
For America, no, it's not possible for me because I'm Russian. I cannot read the papers from Nevada.
No, I mean, Russia has a lot of nuclear reactors, and not a lot of nuclear reactors are also outside Russia.
Yeah.
So it's not necessarily only Rosatom can fund. There are also Ministry of Science funding, Academy of Science funding for research projects. So if you are only specified to Rosatom and there are some restrictions, then I can go to.
No, we have a fundamental project.
Yes, fundamental
And, but it's not industrial.
But
You are talking from industrial.
Concepts are more or less same. The approaches, like you say, the parameterization, the modeling, the approaches are more or less same. So, what I have to do for that? You have to
I think you need to maybe contact me and Vladimir.
Okay.
The email.
Okay. Is there in the email in the website in the PowerPoint?
Yeah. Roman chat with my name.
Anna
First name is Anna.
Yes.
Yeah, and I've written.
So surname is
Yeah. I do both actually. It's actually different one. First of all, yeah, it's not construction, just for conversation with different events. It's quite as well. And then there is this option to see. It was written in graphical because it's from the ASCII files, and you can then load it some original material or something which we usually use.
We can use at least this.
Roman chart. This is my first name, this is my second name. Absolutely. Okay, no problem.
May I have anything which is consumable? Is it to communicate?
It's better to Gmail actually because it's kind of more even in my presentation, we have some references.
I have one request. You have presentation. We all will get your presentation. Yeah.
Yeah.
In your presentation first slide, if you give your email, that will be for everyone.
Yeah.
So there is no need to be confused and take individually.
Yeah.
If in the presentation.
Okay, I will put it down.
Yeah, so that it will be for everyone, not to take individually. Thank you for the lessons.
Thank you for the question.
The migration rates that you mentioned in this is a migration of the results from the exclusions and the accidents, not from the disposal.
It's from disposal as well. It's possible. Actually, as I said in the start, migration is important for the remediation and for the building a safe nuclear waste disposal. When we have experience from this actual contaminated areas, we can then transform it to safe nuclear waste disposal. When we understand, for example, the source of funding for the radiation program, we can understand that when we build new nuclear safe disposal, we need to account that in the future when so, for example,
I would it's close to this, but I'm looking in assessment of water resources with using environmental hydrology.
Yeah.
Oxygen 18 and detail. Do you use this?
Actually, no. Some of our colleagues, for example, next lecture of Natalia will be about radioecology. They use, for example, leak to help, for the
Mapping or tracing?
for the rating of not only pollution, for the tracer of movement, for tracer of bottom collecting, because you can dating of bottom layers using flat and the radioecology usually use
So maybe it's more accurate, maybe than 100%, for example.
Actually, it's not topic of my research. It's maybe more interesting to talk with Natalia because she's involved more than me. But of course, the topic for oxygen for others is quite important for the natural system as well.
Okay, thank you. Thank you so much.
You're welcome. Это естественно, я работаю, я защитилась, у меня аспиранты, да, я уже работаю. Просто вдохновляюще рассказывали, на самом деле. Что-то магистратуру рекламируют. А вы еще магистратуру собираетесь?
Ну, здесь. Нет, я закончила
Уникальный телефон?
Да.
Валентина, да, я даже знаю,
Да, вот
приезжала к нам. Да, мы, кстати, писали однажды совместный молодежный проект с Дарьей Коров. Она работает, у нас Ключука работает, ладно, работает. Вот, у нас даже был такой опыт, совместный молодежный спокойный тогда. Ну, говорят, может, теперь РНФ будет в России подавать, поэтому мы заинтересованы в коллаборации, там, не знаю, в совместных работах, в принципе, с Белоруссией, если вы приедете сюда, да, в общем, мы здесь химией и радиохимией занимаемся. Вам тоже, по-моему, лекции, по-моему, даже экскурсии должны быть. Нет?
Да, вчера проводили, буквально 2 лаборатории показали.
Ну, если что, вот я оставила свою.
Да, мы записали. Спасибо.
Вентилятор у нас теперь на кафедре. Я хочу с ребенком или
Да, тут здесь все какие-то розовые. Вот, потом получается. Так, а тут есть это указка, все.
Все есть, микрофон работает, все есть. У тебя флешка с собой?
Микрофон.
Точно, в папку закинь. Да.
Вот первый. Конечно, вчера начали таскать эти вентиляторы во время практики, но как-то вообще не прикольно получилось.
Как я не буду.
Вот это
Куда это поставить?
сюда.
Во время практикума?
Да.
Не помню.
Ну, ладно.
А, ты имеешь в виду, когда лекция была?
Ну да, да.
Блин, ну они потому что тут подыхали все. Это с радостью. Не поставил.
Угу.
Да.
Вот это. Poco caliente. Poco caliente.
Just your first.
Buenas tardes.
Меня слышно? Good morning. Oh, so good day. Good day. Okay, can I start? Everybody here? Most of all. Yeah? Yes. It's a bit hot today. Oh, no, it's okay. That's nice.
Hello, friends. We continue our course. And today I want to tell you about environmental monitoring near the nuclear facilities and radioactive storages. I will tell you about Russian system of environmental monitoring around, for example, nuclear power plants and other nuclear enterprises. Okay. Every enterprise contaminate environmental by different radionuclides, and but the concentration of them is very, very small. Despite of that, we should control every radionuclide. And of course, it is very, very important if we have some accident on nuclear enterprises, and to understand that everything is okay, we need to control environment before building nuclear enterprises, during the enterprise working, and of course after accident. And you see, and you agree, I'm sure that nuclear facilities are currently the main existing potential source of man-made radionuclides in the environment. It is not real source, but as potential, it is one of the most dangerous source in the world. Comparison of amount of radionuclides released in the environment from various sources, what we have nowadays in the world. The main source of man-made radionuclides released in the environment includes reverse nuclear test explosions in the atmosphere and activities of radiochemical plants for spent nuclear fuel treatment. For example, plant Mayak in Ural in Russia or Hanford in United Kingdom. Here you can see that, for example, from different accidents to the environment, was now in the environment appears a lot of artificial radionuclides with very, very, very high activities. Okay. Properties of the long-lived isotopes of actinides in spent nuclear fuel. I just want to show you that these radionuclides are most dangerous, maybe because they are alpha emitted radionuclides, but the most difficult to identify, yes, because it is very easy to identify the gamma emitted radionuclides, and very, very difficult to find and identify alpha emitted radionuclides. But before, you need to make a radiochemical separation.
Yeah.
Okay. It's just, I just want to show you that nowadays in the environment and every sample that you can take, exactly my T-shirt, we can find artificial radionuclides everywhere they're existing. For example, here you can see the amount of cesium-137 that existing now in the ocean after the Chernobyl accident, Fukushima accident, and global nuclear weapon testing. Okay, it is maybe everybody knows that, but nuclear power plants in the world are located exactly in North America and Europe, and it is important that all of them, most of them, located in the north part of the Earth. That's why really the north part of the Earth is more dominated than south. It's very interesting that Russia have only 10 nuclear power plants. Only 10. Very, very big country, but only 10 nuclear power plants.
They're smart people.
Mm.
But is it present status? 10.
10, yes.
But I read 18 or 19 functioning.
Where you found this information? It was 11 nuclear power plants, but one was closed 5 years ago, and now in Russia located only 10 nuclear power plants.
Excluding the research reactors.
Excluding, of course, a lot of research reactors.
51 research reactors.
Yes, research reactors, a lot of research reactors Russia has, but nuclear power plants that are working for and produce energy, only 10. This is number of reactors in operation worldwide, and the leader of number of reactors is the United States of America. The second place goes to France, third to Japan, and Russia Federation. Only the fourth place in the world. Latitudinal distribution of plutonium clouds due to the nuclear weapon test in the atmosphere. Also, that I said before, the most part of radioactive contamination located in the north part of the Earth because of accidents, because of nuclear weapon tests, and other reasons. Okay. Environmental monitoring contents. What should we analyze before, for example, or during nuclear power plant working? Natural conditions, air, soil, vegetation and fauna, local foodstuff, aquatic ecosystem, hydrobiological and ichthyological parameters. All of these types of samples should be analyzed and should be understand the amount of radionuclides. Later I will show you radionuclides that are most important and not so important. And what control during the every process, during the facility working is equivalent gamma dose rate and individual dosimetry of employers. The share of radionuclides released into the environment during the accident of the Chernobyl nuclear power plant. Why it is important? It is important to understand because of these, after this explosion, the monitoring system was renewed. Because first was exploded gases and krypton, xenon, and iodine 131. And that's why nowadays, near any facility, people control these gases. And all these gases, except krypton, are artificial. Krypton 85 exists in the air, in the space, and can fall down from the space. But the amount of it is very, very small. It's very difficult to. But everybody should remember that krypton exists in the space, because if you measure these gases near the nuclear facility and found krypton, it can be not artificial. It can be from the space. And to understand is it artificial or not, you must measure the background before. Measuring background every month to understand these gases amount. Of course.
So in order to understand this, it is artificial or not. So we will measure the background before we build the nuclear power plant.
Or other facility. And the problem is that usually only one equipment used to catch all these gases together. And it is very, very difficult to separate these gases. And that's why too important to measure these gases before constructing anything nuclear. Yeah. But usually the amount of krypton is very small and really difficult to identify. But for you as a radiochemist, you must know such things. Other radionuclides that now are most measurable during any nuclear facility work. Cesium, strontium, sometimes plutonium, and for example, wait. Okay. I just want to show you some pictures, okay? Or maybe not in the system, but for example, this is building nuclear power plant in Bangladesh that nowadays Russia building in Bangladesh. And now they built 2 reactors there. And I will show you the monitoring system around this construction. For example, this is the location of food markets near the Rupur nuclear power plant. No need to take a lot of samples, really, no need. The statistic shows that really if you take 2 or 3 samples, it is enough. If you find something there, you can and should take more samples. But for example, when I'm working in the field and take grass or bottom sediments, we usually take 2 samples, 2 columns, 2 fish, for example. And really, according to the experience, it is enough. 5 points is enough.
The closest distance from Earth distance.
This is 30 kilometers circle. Inside the 30 kilometers. Of course, if you find something in your samples, you will discuss and make decisions about other investigations. Okay, it is just an examples. You can buy food in the markets. When I worked in Chernobyl, but in Russia side, but the zone was Chernobyl has such status, Chernobyl zone. I really bought some mushrooms on the market and found so many cesium that I have never seen in my life. Yeah, and it was mushrooms in with salt for just food. And they eat it normal. No. Okay. Okay, what should we control? It's a dose rate that should be also controlled, as I said. And usually it looks like this, and distance from nuclear power plant. The enterprise is in the center of the circle, and you with the zenither is going to different routes and just fix or write, yes, and the zenither equivalent dose rate. It is also normal monitoring every month In every enterprise, they're doing that. And individual dosimetry. You can find persons who live near the nuclear power plant, give them dosimeter and said that they should eat with it, sleep, and do anything during 1 month. This is normal ecological monitoring. But it should be done. Okay. After that, when you understand the dose rate around your facility, when you understand the background of gases and the background and for persons, individual, you can go to the field and collect the samples. How we make air monitoring? Every month we collect aerosol filters. These equipment working like a pump that count exactly the volume of air that is going through the filter. And you can use very, very simple analyzer, alpha beta, for example, and understand is it any alpha or beta radionuclides on your air. Also, you can collect rain or atmospheric fallout. Usually we use just a plant table because the square is constant. If you have a constant square, yeah, you can collect the fallout, then ash it and measure. And you can calculate contamination per square. Of course, snow or rain, you should collect in vessels. Here, for example, you can see real points of atmospheric air sampling in the Rukur nuclear power plant region. 8 points. Really, it's enough. 1, 3, 5, 10 kilometer radius from Rukur nuclear plant site center. 2 or 3 points in each circle. Of course, to collect air samples, you should know well the wind type of wind, but really it can change. And you must sampling around in different routes. Okay. Soil monitoring. When you sampling soils, you should understand that usually the most part of radionuclides consists of organic top layer. Usually sampling are going slightly per one centimeter, but really to understand the ecological situation, you can just sampling the organic horizon and mineral horizon to understand how deep your radionuclide migrates. It is for the first investigation, just for the first monitoring. Of course, after that, when you understand where is radionuclides existing more, you can sampling it in more details. Vegetation monitoring. It should be also done very carefully. 2 or 3 types, most common types of vegetation in the place you are walking. And usually we ash it and make a gamma survey. But Sometimes, if you find something interesting, you can separate your vegetation to the roots, stems, and leaves, and understand the distribution of radionuclides through the vegetation body.
Just a question. Do you want to gamma
I will show you later about analysis, okay?
Yeah.
For example, mammals, phytoplankton, zooplankton, and fauna monitoring. Fauna monitoring is also important. Here you have to know only one thing, the most important thing, that when you analyze first time the fauna, any type of animal, you should analyze that part of animal that can be eaten by persons. Meat from cow and other. For example, in the fish, first analyze only back, because only back is eaten. And after that, if you find something, you can analyze in more detail. Okay, this is scheme of water sampling in the Rupur nuclear power plant here in the river. And water. Water is very, very important part of monitoring. And surface water and underground water, and everybody should be very careful about water because soluble radionuclides that exist in soluble form are most important in the radioecology. Okay. Now about the problems with the environmental samples. Environmental samples consist of very small amount of radionuclides, and you should concentrate the samples. For example, water. When you're working with water samples, usually in Russia we use the co-precipitation method for concentration radionuclides. For example, here you can see the iron plus 3 hydroxide co-precipitation. This method is very, very useful for all types of actinides and most of radionuclides. If you need to understand the amount of actinides, plutonium, neptunium, americium, curium in water, this way is the best. It really works. You can make the co-precipitation procedure during your field investigation. Also, you can take your samples, hundreds of liters. Usually, you need hundreds of liters to find anything, and make a co-precipitation procedure in the lab. For example, for technetium 99, you usually use iron plus 2, but iron really works, and this is most popular and most useful method to concentrate radionuclides from water. Here you can see the principal scheme. Never forget about tracers. When you analyze any environmental sample, we want to understand the amount of any radionuclides, you should add tracers. We usually use for uranium 232, for plutonium 236, for americium 243. Okay. But here I just want to show you that you must also be careful if you work in pure water or seawater. Different types of sample makes you different types of problems. For example, magnesium is the biggest problem of the seawater, and it can make a mistake in your measurements. This is just for you to know the technician concentration separation procedure method. From water.
How can you solve the model?
It makes more sediment, and it makes problem when you separate actinides, because resins are usually the capacity of resins is constant, and magnesium can put in the place of actinides in the resins. But usually when you're working with seawater, you should separate magnesium as well. But usually you should separate, for example, all salts from environmental samples first with co-precipitation with calcium phosphates, for example. Yeah, radiochemical procedures are very, very unique for any radionuclide. And when you work with environmental samples, you should be very careful. Okay, this is about technician. I don't know. Technician is usually not included in normal monitoring system, but technetium is one of the most interesting radionuclides now in the environment, because it is difficult to identify. Very, very small amount of laboratories in the world are identifying technetium, but it is really exists as plutonium everywhere now, technetium-99, in very, very small amount, but it exists. Okay, fish. Here with my colleagues from Japan, investigated fish. As I said before, first sample, first fauna samples should be analyzed only in places which can be eaten by people. Radionuclides migration pathways in the environment, why it is important to investigate. This is a typical scheme of radionuclides migration pathways in the lake, for example. When a radioactive waste is going to the water, it is put down very, very fast and concentrate in bottom sediments. For example, now, after Fukushima accident, the amount of radionuclides that exist in the soluble form in the sea is very, very small amount. Why? Because most of radionuclides are in bottom sediments. The concentration of radionuclides in bottom sediments can be more than 99%, and only 1% exists in other parts of aquatic system. This is very important. Usually, if you can find anything in bottom sediments, it is no need to try to find radionuclides in other objects from the lake. Do you know about biological half-life? Yes, of radionuclides. It is also an interesting thing that, for example, biological half-life of cesium in the fish that are living in radioactive contaminated lake equal to a cesium half-life. But if you take your fish and put it to the clean lakes. The biological half-life will be 2 months. Yeah, it is important to understand that only fish that eating and living in contaminated lake also contaminated. If you take it to the clean place, it will clean very fast. Okay, radionuclide migration pathway. Bottom sediments, phytoplankton, zooplankton. Here you can see the effect of amount of radionuclides. Most of radionuclides consist from bottom sediments and phytoplankton, zooplankton, so benthos, roach, and pike. Roach, for example, lives near the bottom sediments and eating parts of sediments. That's why it is contaminated. But, for example, pike eats only roach, and that's why it's not so contaminated. Very important to understand with what are you working, with what type of fish, what type of animal, where the animal live, what it eats, where it sleep. Everything is important in environmental monitoring. And you have to understand the type of fish, what you have to investigate. Interesting thing that phytoplankton accumulates more radionuclides than zooplankton. We think that it is because the surface square for phytoplankton is more than zooplankton. Maybe that's why it accumulates more. Okay, also, maybe you can see well, but radionuclides distributed between fish organs in not equal conditions. For example, most of radionuclides, more radionuclides exist in surface organs, gills, scales, and in entire organs exist less radionuclides. This is plutonium and americium, for example. You see becquerels per gram. We investigated the radioactive contaminated objects. Zooplankton, phytoplankton. If you, this is chironomids investigation. Chironomids. Do you know that insects, camari, I don't know exactly, mosquitoes. Yes, they produce their life in the bottom sediments, in the lakes. And the babies of mosquitoes and chironomids, and they are living in the bottom sediments. And if the bottom sediments is very, very contaminated, the mosquitoes babies will be contaminated. It is interesting. It was really one investigation. One scientist investigated mosquitoes that lives near the contaminated reservoir, and it found that the mosquitoes that was born in that radioactive contaminated reservoir was really contaminated. It really cannot contaminate persons, but it is detectable. That mosquitoes can be detectable. They are really contaminated, and it is just because they produce their life in the bottom sediments. And bottom sediments is the most contaminated object in the radioactive reservoirs. Usually in biological monitoring, we use concentration ratio factor. It means activity concentration of biota, whole body, divided to activity concentration in water. And this concentration ratio is very, very, very useful. A lot of investigators in the world understand the radiological situation according to this factor. Okay. Best radiation markers, mushrooms and leeches. You maybe know that, yes, but it is very interesting that leeches, for example, they have no roots, and that's why you can find only atmospheric radioactive contamination when you investigate leeches. The problem with it is that you really cannot understand what lesion is alive and what lesion is dead, because after death, lesions looks like really alive. Yeah, that is a problem, but it stopped contaminate. Only mechanical particles can stop, but as a vegetation, it doesn't contaminate. You understand? Take radioactive materials from the air, but then the lesion can lie on the surface 20, 30 years, but you cannot understand is it alive or not, and only specialists can see. That's why the most popular mushrooms. Yes, because it really accommodates a lot. Okay, sample preconditioning. What we are doing first? Take sample, ash, and acid dilution. It is the most simple way to investigate everything. Then filtrate and measure.
Excuse me. I have a question. As you know, the cesium is generally looking in. There are some other elements that cesium is the most popular in mushrooms.
Yes.
It's also liquid in the room temperature. And when you keeping it or drying overnight in the ether, is there any loss in activity?
If you wash?
No, if you burn.
If you burn? Depends on the temperature.
Which temperature is acceptable after which level?
If you want to save the cesium, you must stash less than 600. Yes, but if you want to lose, nowadays, first sample that should be monitored usually measure for these gamma radionuclides and 1 beta. For example, in Bangladesh nuclear power plant, during the constructing the reactors, they measure only these. If some of these radionuclides are higher, it should be discussable to make more detailed investigation. But in Russia now, you have to measure only these 5. That's it. And gases, as I said before. Okay, separation methods, usually used for alpha, precipitation, solid extraction, ion exchange, and extraction chromatography. Really, these methods, precipitation or co-precipitation and solid extraction, these methods are using for concentration samples. Yes, solid extraction is most common concentration method in 20th century, and co-precipitation as well. And after, you can use ion exchange or extraction chromatography resins to separate radionuclides that you want to investigate. In 21st century, it is really convenient to investigate everything. You can buy resin for any radionuclide you want. For example, true transuranium for plutonium, americium, curium, other, and Teva resin, uranium tetravalent or just tetravalent resin for thorium, uranium, and all the resins consider two oxidation states of radionuclide you investigate. All these methods really useful and not very difficult to make. In environmental sample, the biggest problem is concentrating. Because maybe as you know that, for example, plutonium exists in the environment in different oxidation states. And that's why also it can exist in different oxidation states in the grass as well, and of course in the water and soils and in the mammals as well. And you should collect your sample, concentrate plutonium, and after that change the oxidation state, and after that it should be sure that the oxidation state is, for example, 4. And only after that you can use Teva resin, for example, to separate plutonium. For americium, for example, it is more simple because it exists only in one oxidation state, 3. For thorium, it is also not very big problem, because thorium exists only in oxidation state 4. Okay. And after that, you can make analytical methods for solid characterization. What we are doing here with any types of sample that you can do, alpha track analysis, maybe Irina said about that in the morning. Electronic microscopy to understand morphology, measurement composition, since isotope composition, XRF elemental mapping, and other. Maybe okay, optical microscopy, alpha microscopy. When I talked to you about chironomids, I said that we was found that chironomids accumulates a lot of radionuclides because of alpha track and microscopic analysis. Because before the using these methods, we just understand that chironomids, we see that in detector they show the activity. But we thought that activity is inside the mosquito. And after using such methods, alpha track and microscopic methods, we saw that the mosquito and chironomida doesn't exist radionuclide contamination inside. It was just small, very small parts of bottom sediments that was stick on the surface of chironomid. This is also important. Why? Because if you find, for example, radioactive contamination on grass, vegetable, food, and other samples. First, what you should do, you should wash the food or vegetation or something else, because the contamination can be just surface contamination. And it is normal, usual situation when somebody finds dust on the vegetation, and but tell us that the grass is really contaminated, but it's just dust. You can just wash the food and understand that everything is okay, or not. Or if contaminated is inside, it can be a big problem. It means that the soil is very contaminated, and the vegetation accumulates radioactive materials from the soil or from the water. And sometimes washing doesn't help. And that's why, of course, it is good if you have just optical microscope to take a look to the surface of your sample to understand where is contamination. Solid analysis. Scanning electronic microscopy for more detailed analysis. Okay, hot particles. Irina said about hot particles in the morning? No? Yes. This is usual method for analyzing hot particles. Hot particles. Interesting thing, but really after Hiroshima and Nagasaki, nowadays on the beach in Japan, you can find hot particles. Today, you can go to the beach in Japan and find hot particles. But near Fukushima, you cannot. But in Hiroshima, you can. Also, for example, you take the soil sample and find some radiation there. What should you do first? You should divide the sample into parts and measure 2 parts of soil. If one of parts has high contaminated and another low, it means that you find hot particle in that sample. If you find a high contaminated part of soil, you should divide it 2 parts and measure one more time, divide, and find hot particle. Some scientists think that hot particle is not a big problem because it can be dissolved inside the human organism. But some scientists think that it's dangerous because it emitted radioactive and can affect the internal organs. But it's a special thing. Okay, this is my finished slide. I talked less than 1 hour and 15 minutes. But I think everybody happy about that. Because I really don't know what should I say to you. The environmental monitoring in Russia is very simple now, but is only gamma and beta emitted radionuclides first. But we do it very often, every month, near all facilities. And Russia Structure Rosatom has an internet site where they show all information about all enterprises. I don't know exactly true information or not, but they show. Of course, I'm also really sure that alpha-emitted radionuclides must be included to the monitoring systems. But to investigate alpha-emitted radionuclides, the staff should have a high education level. It is very difficult. But nowadays, plutonium and, as I said, technetium, americium exist in the environment. And in every sample you can find, ever in soils, exactly in soils. The question is the amount of plutonium, but you can find anywhere. For example, americium. Americium is the decayed product of plutonium. For example, plutonium-241 has half-life 14 years. And after the nuclear tests in 60s, last century, a lot of plutonium-241 was fell down, but now decays. And we have americium, the product of plutonium. And the amount of americium-241 increase every month because it is decay product, and the americium half-life is 400 years. And americium is artificial radionuclides. It never exists in the environment. And after, I think, 10, 20 years, we will use americium instead of cesium, because cesium decays and americium amount increase. Yes. I think that's the only question. I don't hear you. First burn. Yes, but the scheme, yes, really, first of all, gamma, non-destructive method. Just take everything and whack, yes, to standard geometry, meat, fish, grass, so, and just estimate on gamma. Is anything there? After that, burn, of course. Burning. Why we burn? Huh? Acid. It's just because to separate actinides, it is impossible to separate actinides from solid. Only from solution you can separate. You have to make a solution from your sample. Solid, it's not destructive analysis, only gamma analysis. For example, if you want to investigate strontium, you should dissolve your sample. You cannot find strontium in solid. You should separate yttrium, strontium, and first burn burn to concentrate and make mass smaller, and then dilute in acids. Acids you use for beta and alpha emitted radionuclides. You never find it using gamma spectrometer. Never see plutonium in gamma, or neptunium, or curium, or something else. Yes.
I'm just curious that if you are working on any project that's simulating accident case and environmental effect on a simulation, another gathering samples and measuring it. Because as much as I remember that SK staff from Belgium was developing a code named Erika. Have you heard it?
Of course.
Yeah, but I don't know that they are developing still or using and after that, if you are working on a project or
Yeah.
if you are using any code like this.
Yeah, it's a special topic, modeling. Yes, modeling is imagination and fantastic thing. Every
Sometimes
yes, of course. Every model needs real data.
yes.
Yes.
Yeah, but for accidents,
Yes, of course. During the nuclear facility constructing, and as all people in the world and Russia as well, using different software to modeling accidents. In IAEA, they have recommendation about software what we should use, and exactly it is not the name of exist software. It's parameters. That software should accord to. I can show you these parameters, but it is not very strong. Erica tool is very very useful program. Why? Because it uses circle for any object. Yes, it is to calculate the dose that animal or human on everybody can accumulate. Yes, but it's really useful only for turtle and for fish. Yes, it is very bad for horse, for example, but it used Erica tool. I know a lot of software that can be used, and I know according to the law, you can use your own program, your own software, that you will write. It just you just need to know these parameters of EIEA. It is only 3, as I know, parameters about statistical.
Share the parameters. They are not sharing code or publishing in code. No.
No.
Just they share parameters.
Yes. They just share parameters. Yeah. Exactly. Yeah, but of course I know, Erica. When I worked in radioactive contaminated reservoir, we used Erica because for fish it is very good, and we calculated the dose for fish, exact dose, and Erica was best. Yes, but for cows, for rabbits, it is not so good. Yeah, for human, it is not so good. And really, in nuclear, Russia produced also software. And now Russia constructing the nuclear power plants in Turkey, Egypt, as I know, Bangladesh, Uzbekistan, and Rosatom using their own software. I don't remember now the name, but I'm sure that I know exactly that they use their own software that was written here in Russia by Russian programmers, and EIAA approved that. Yes, I think really I think that modeling is in the beginning of the route, and the humans in the world should discuss and make the choice what we should. I don't know, really.
I think the best is to validate the program of the code, the normal operating conditions, and then you can model the accident scenario, because it's not really possible to validate the accident scenario for the code. You answer what I mean?
Yeah, well, that it is really impossible to modulate all scenarios.
Yes, that's what I'm saying. If you validate the code with the normal operating conditions case, then you can say that, okay, this code works well, then the accidental scenario, okay, it's not a 100% true correct way, but you can just make estimation that okay, we can also work this code for the accidental scenario.
Yes, I agree. Why not? But modeling is not my favorite topic. Okay. Too many software, yeah, too much, and I really can't say this is better, this is worse. I really can't do it. I think it's math question for mathematics, and. But the main question of constructing radioactive facilities is not accident modeling. I think the first question is geographic conditions. Geographic condition, mountains around, the water near, yes? Because Fukushima shows that the nuclear power plant was built near the sea affected less than Chernobyl, yes, because radionuclides went to the bottom segments very fast, yes. It is important for the humans. Geographic condition first, as I think. Thank you very much.
Oh, right.
Okay.